Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
This video lesson is an introduction to structure and reactivity, particularly organic acids and bases. So there's a variety of definitions that have arisen to describe acids and bases, and so we'll go through them one at a time. We'll be discussing here acid dissociation constants, pKa, assessing the relative strengths of acids and bases, how to determine the position of equilibrium in acid-base reactions, and we'll be doing a couple example problems along the way. So to start out, the first useful definition of acids and bases was put forth by Arrhenius, and in this definition, an acid is a substance that dissolves in water to produce H plus ions, whereas a base is a substance that dissolves in water to produce OH minus ions. Now, today we know that it's not accurate to refer to an acid as giving rise to simple H plus ions. So an H plus ion immediately combines with a water molecule to give a hydronium ion, and then hydration of the hydronium ion itself gives the ion H5O2+. However, throughout the rest of this lecture, we're just going to be representing a proton dissolved in an aqueous solution as a hydronium ion, H3O+, although it's an oversimplification. Now, this Arrhenius definition of an acid and a base is still valid and useful today as long as we're talking about aqueous solutions, but we can expand the definition a bit more to incorporate a wider variety or more general class of molecules. Thus, we have the Bronsted-Lowry definition of acids and bases. So, with this definition, we have that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So, by this definition, an acid-base reaction is a proton transfer reaction. So, for most of the rest of this lecture series, I'm going to be focusing on this Bronsted-Lowry definition of an acid and a base, and therefore the conjugate base and conjugate acid forms for proton transfer reactions. And then at the very end, we're going to briefly talk about the Lewis definition of acids and bases. So, according to the Bronsted-Lowry definitions, any pair of molecules or ions that can be interconverted by transfer of a proton is called a conjugate acid-base pair. When an acid transfers a proton to a base, the acid is converted to its conjugate base. So here the acid is HCl, transferring a proton to the base, which water here is in this example, generating the conjugate base Cb of the acid, the Cl minus ion. And when the base accepts a proton, when the water accepts the proton from HCl, it's converted to its conjugate acid form, Ca. So again, it's very important to remember that the members of each conjugate acid-base pairs here differ only by a proton. Now we can show the transfer of a proton from an acid to a base by using curved arrows. So for acid-base reactions, we write the Lewis structure of each reactant and product, showing all valence electrons on reacting atoms. We then use curved arrows to show the change in position of electron pairs during the reaction. The tail of the curved arrow is located at an electron pair, either a lone pair or a bonding pair, as the case may be. The head of the curved arrow shows the new location of the electron pair. So relocating this electron pair here forms a new OH bond, and relocating this electron pair in the bond breaks the HCl bond. Thus, in the reaction of HCl with water, a proton is transferred from HCl to H2O. In the process, an OH bond forms and an HCl bond breaks. It's important to keep in mind that the arrows indicate the movement of electrons and not atoms. So in the previous example, we illustrated the application of Bronsted-Lowry definition using water as a reactant. Now this definition doesn't require water to be a reactant though. So in this example, we have a reaction between acetic acid and ammonia. So the acetic acid on the left here is the acid. The ammonia is the base. CH3COO minus is the conjugate base form of acetic acid, and NH4 plus is the conjugate acid form of ammonia. Now we can use curved arrows to show how this reaction takes place, just like in the previous example. So the curved arrow on the right shows that the unshared pair of electrons on nitrogen becomes shared between nitrogen and hydrogen to form a new hydrogen-nitrogen bond. At the same time that the HN bond forms, the OH bond breaks, and the electron pair of the OH bond moves entirely to oxygen to form O- of the acetate ion. So the overall result of these two electron pair shifts is the transfer of a proton from acetic acid to ammonia. Now let's make it a little bit more complicated. So thus far we've dealt with Bronsted-Lowry bases that have only one site that can act as a proton acceptor in an acid-base reaction. And many organic compounds have two or more such sites. So here we're going to discuss compounds that contain a carbonyl group in which the carbonyl carbon is bonded to either an oxygen or a nitrogen. Now the principle that we've developed here is extremely important and applies to other types of molecules as well, but generally the more stable the charged species is the one in which the charge is more delocalized. So relative charge delocalization can often be understood by considering resonance, and so there's going to be a full video, a separate video on that, but we'll just talk about it briefly. So let's consider first the potential sites for proton transfer to an oxygen atom of a carboxylic acid like acetic acid shown here on the left side. So proton transfer to the carbonyl oxygen gives the first result. So we'll call this cation A, whereas proton transfer from H2SO4 to this hydroxyl oxygen is going to give us cation B. So now we'll look at each one of these cations and determine which is the more stable or lower in energy. So for cation A, we can write three contributing resonance structures. Two of these place the positive charge on oxygen and one places it on carbon. So we'll call these structures 1, 2, and 3. So of these structures, A1 and A3 make the greater contributions to the hybrid because all of the atoms in each have complete octets. In A2, this makes a lesser contribution because its carbonyl carbon has an incomplete octet. Therefore, on protonation of the carbonyl oxygen, the positive charge is delocalized over 3 atoms with the greater share of it being on the 2 equivalent oxygen atoms. Now I say equivalent, they weren't equivalent before protonation, but they are now. On the other hand, if we look at cation B, for which we can write 2 resonance contributing structures, we can see that B2 makes at best only a minor contribution to the hybrid because of the adjacent positive charges. So that's on the carbon and the oxygen here. Therefore, the charge on this cation is in effect localized on the hydroxyl oxygen. So from this analysis of cations A and B, we can see that the protonation of the carboxyl group occurs preferentially on the carbonyl oxygen as opposed to the hydroxyl oxygen because that cation has a greater delocalization of the positive charge. Now again, this is somewhat of an abstract example, something you may not have seen before, but generally this is just to really show you the importance of delocalization of charge for the stability of a charged species. And so you'll be able to tie this in later with the relative strengths of conjugate acid and base forms. Now, in the previous examples, we considered proton transfer to atoms having a non-bonding pair of electrons. The proton transfer reactions also occur with compounds having pi electrons. So, for example, these are the pi electrons of carbon-carbon double and triple bonds. So the pi electrons of the carbon-carbon double bond of 2-butene, for example, will react with strong acids such as H2SO4, H3PO4, HCl, HI, or HBr, as I have written out here, by proton transfer to form a new carbon-hydrogen bond. Now, the result of this proton transfer reaction is formation of a carbocation, or species in which one of its carbons has only 6 electrons in its valence shell and carries a charge of +1. Now, you'll see later on in organic chemistry classes, you'll study the formation, the structure, and the reactions of these carbocations in detail. However, we can do another example that ties in a bit with where we were talking about before of what would be the most stable species to find in this kind of reaction. So, similar to the previous example, the reaction of 2-methyl 2-butene shown here with HI can react in principle to form 2 different carbocations. And so what would they be here? This is not a symmetric alkene like in the previous example of just 2-butene. And so what are those going to look like? So proton transfer to carbon 3 of this alkene gives a tertiary carbocation, where proton transfer to carbon 2 gives a secondary carbocation. So the first here is the tertiary, the second is the secondary. Now what you'll find later in subsequent organic chemistry classes when you're talking about reactions with carbocations and stability of products is that the more substituted carbocation is going to be the more favorable product. In this case, it would be this tertiary. But this example is mainly just to show how pi electrons can act as Bronsted Lowry bases, not just considering lone pairs or non-bonding pairs of electrons on molecules.